Okay, so welcome back, everybody. Um, so I had a little bit to tidy up on when it comes to change of variable stuff. Um, so the main thing that we hadn't done is do an example of what happens when you actually have to come up with the transformation on your own, and what a problem like that might look like. So to give you an example, um, let's try to evaluate the double integral over some region R of 7xy dA. So that's not too bad of an integrand. But R is this kind of annoying region. So where R is the parallelogram, or I should say it's like the closed parallelogram, right? That's the closed parallelogram bounded by lines. Let's see, 2x plus 3y is equal to 1. 2x plus 3y is equal to 3. X minus 2y is equal to 2. And x minus 2y, that's a minus, is equal to minus 2. Okay, so what does this R look like? Let's draw it real quick. Okay, so we're kind of just going to sketch this thing here. So it's bounded by these four lines. So 2x plus 3y is equal to 1 and 2x plus 3y is equal to 3. Those look something like this. Well, maybe I'll draw this piece of it like this. Okay, so that you can, so I'll extend both of those. Those are pretty bad lines. So they look something like this. And then the lines, so we'll say this is 2x plus 3y is equal to 3. And this is 2x plus 3y is equal to 1. Okay, the other two lines, x minus 2y is equal to 2 and x minus 2y is equal to minus 2. Those things look like this. So at least the pieces here. So this is what the line x minus 2y is equal to minus 2 looks like. And x minus 2y is equal to 2 looks like this. And so R is the inside of that region. Maybe I'll use a different color pen here. Okay, so here's R. Okay. And so, what is the problem with this R? Why is it annoying? Oh, so I see in chat that the last lecture is still unlisted. Yeah, that's I'll do that. So I've always tried to do that right after lecture. I just forgot to do it last time. But if that ever occurs in the future, you can still access it from the link in the announcements. It's just a little bit annoying. I know some people access them that way anyway, so those people wouldn't even notice a difference. But yeah, I always try to make them public for that reason, in case you're just using the YouTube channel, which is more convenient anyway. So yeah, I'll do that right after lecture. Okay, so this is what my region R looks like. This region is a little annoying because if I wanted to actually do a double integral of this thing, because I need an upper and lower function, and because my upper and lower function is going to be piecewise defined here, I would have to split this R, right, into a couple of pieces. So if I split it here, right, I could do upper and lower. And then on this next piece, I would split here, and I could do upper and lower. And then on the last piece, I could do upper and lower. Okay, so that would be annoying. I'd have to split this into three integrals, and that would take me that would take me a lot of time, so I don't want to do that. So I want to use change of variables here. But how do I do that when I'm not actually given, this is the entire problem, I'm not given anything else, so no transformation to a nice region. So what is your hint, right? What sort of intuition should you have? So remember that what we are trying to do is we're trying to come up with a region in the UV plane, and that is some UV plane, right? So we're trying to come up with a region in some other plane described by two variables that is nice, all right? Ideally, it would be simple, or at least vertically simple, so that we could do this integral in one go. And then we need to find a transformation that takes that nice region to the region that we have here, R. So you might say, oh, well, then I have to kind of think backwards. Well, doing it purely visually is pretty hard to do in general. So the algebra should tell you what it is that kind of has to happen here. Okay, so do you see in the boundary of R here, so it's bounded by these four pieces, do you see something you could do, a substitution you could make, that would immediately make this a nice region? Okay, well, so I have two lines, and the left side of the equations of these lines is the same expression, 2x plus 3y is equal to 1, 2x plus 3y is equal to 3. So the left-hand side, 2x plus 3y, is the same for these two lines, and the left-hand side of this equation is the same for these two lines. Okay, so what if we did the very straightforward thing and just said, well, what if I let u be 2x plus 3y, and I let v be the other thing, x minus 2y here? Okay. All right. Well, this describes a transformation. Okay. This describes a transformation, but the transformation it describes, well, I'll talk about it here in a second. If we just apply this to R, what do these boundary lines become? So if u is 2x plus 3y, this becomes what? Right? So 2x plus 3y is equal to 1. That piece becomes what? Since u is 2x plus 3y, this becomes u is equal to 1. 2x plus 3y is equal to 3. No. That's a 2. 2x plus 3y is equal to 3. What does that become? That becomes u is equal to 3. The last two pieces, x minus 2y is equal to 2. What does that become? That becomes v is equal to 2. And x minus 2y is equal to minus 2 becomes v is equal to minus 2. So now these lines that are not horizontal or vertical go to vertical lines and horizontal lines here, right? And so what is the region in the UV plane that's associated to this? Well, let's my region in the UV plane. So here's U, here's V. So we have lines U equals, let me get a straight edge so that my lines aren't so awful. Okay. So we have just to remind you, we have the lines U equals 1, U equals 3, V equals 2, and V equals minus 2. Okay, so U equals 1. There's 1. Here's 3, we'll say. Here's minus 2. And here's 2. And so what is this? So I have vertical line, vertical line, and horizontal lines. So that this region, this rectangular region, is my S. Okay. All right, and you can just see, right, the bottom is V is equal to -2, the top is V is equal to 2, the left is U is equal to 1, and the right is U is equal to 3. Okay. Now, you might say, oh, great, right? We found the region in the UV plane that maps to R. So then we found our transformation T, and we're good to go, right? We see that this is a very easy rectangle. I can do this integral in one go. So we're good to go, right? What's the problem here? Let me bring this back. Okay, so here, maybe let's arrange it like this. What is the problem with what I have written here and the relationship that this has as far as R and S are concerned? Well, what kind of transformation did I define here? I'm tempted to call this T, but what's the problem with this transformation versus the transformation that we've done previously? Well, we have written U and V in terms of X and Y each. So this transformation that we've boxed here takes R, takes in X and Y, and spits out U and V. So it doesn't map from the UV plane to the XY plane. It goes in the other direction. It maps from the XY plane to the UV plane. So this transformation we wrote does the opposite. It maps in the opposite direction. It maps from the XY plane to the UV plane, but that is not what we have written in change of variables. Okay. So how do we fix that? The problem is this transformation is going in the wrong direction. It's going from the XY plane to the UV plane. How do I correct that? Okay. So here is where, if you have had, say, linear algebra, then you will probably have, so if you've had Math 240 or 461 here at UMD, then you might have already guessed what it is that we're going to do here. What we're going to do, basically, is we're going to compute the inverse. Now, I'm not implying that all these transformations are always going to be linear. So in some instances, they won't be. But the idea here is that in a lot of these instances where you're coming up with your own transformation, they will be linear. And when that's the case, whatever it is you're doing here is actually computing the inverse to that linear transformation, right? So this is like finding a matrix inverse. Okay. And so if you wanted to use those tools to do it, you're welcome to do so, but you're going to be able to do this just in the way that I proceed here, which is equivalent to that. So I have this transformation defined as U is 2x plus 3y, and V is x minus 2y. So what do I need to do? I need to solve for x and y in terms of U and V. Because that's how my transformations are always given, right? That's how my transformation was mapping from the UV plane to the XY plane, so in the other direction. How do I do that? I have this linear, this system, I can think of it as. How do I solve these in terms of x and y? So, how do I solve these for x and y? So you can proceed just like you would if u and v were numbers, if you like, right? You have a simultaneous system, these two equations and these unknowns x and y that you're solving for. So how can I do this? I can just do simple Gaussian elimination if you like, or in this case, since there's only two of these equations, it's pretty simple. I can eliminate one of the variables. So let's eliminate x here. So if I want to eliminate x, I could subtract from u 2v, right? If I multiply v by 2, I'd get a 2x here, so I'd get 2x minus 2x, that'd be 0, and then what I would have left would just be in terms of y. So u minus 2v is what? This is 2x plus 3y minus 2 times x minus 2y, which is 2x minus 2x is 0, so 3y minus 2 minus 2y, so that's 7y. Okay. And if I want to say, so if I want to say, get a relationship between u and v by eliminating, say, the other variable, well, I could multiply u by 2 and multiply v by 3, so that I would get 6y minus 6y. So I could add those together. So this is not the only way to do this, but any way that you go about this is basically equivalent. So what am I doing here? If you've seen Math 240 material, then you'll notice that we're doing row operations here on this matrix, and that's what's going on here. This is basically us keeping track of row operations. So this would be 2 times 2x plus 3y plus 3 times x minus 2y. Okay, and so I would have 2 times 3y is 6y, 3 times minus 2y is minus 6y, so those cancel. So I'm going to have 4x plus 3x, so I'm going to get 7x. Hey, that worked out pretty nice. Okay, and so what does this mean? It means that x is equal to, if I divide through by 7, so this is 1/7 times 2u plus 3y, or sorry, 3v, and y is equal to 1/7 times u minus 2v. Okay. So if, again, as I said, you've had 240 or 461 at this point, then you're going to have no issue seeing exactly what it is that's going on here. You've actually also probably guessed what it is that happens when we compute the Jacobian, right? So the hint is, well, this isn't the hint, this is just telling you exactly what it is that the Jacobian of this thing just becomes the determinant of that coefficient matrix. So that's what's going on here. Okay. So now we have found our t that gets the job done. And you can check yourself that defining the t in this way takes this s in the uv plane to this r in the xy plane. Okay, so now we've found the transformation. We have the region that we're going to be integrating over that's very nice. So now I need to compute the Jacobian of this thing. So let's do that. So the Jacobian of this transformation is, so if I, my way of remembering here is that this is the determinant of x sub u, x sub v, y sub u, y sub v. So this is x sub u times y sub v minus x sub v, y sub u. And we can do this just in our head here. So what is the u partial of x? It's going to be 2/7. So this is 2/7 times the v partial of y, which is minus 2/7 minus the v partial of x, which is 3/7 times the u partial of y, which is 1/7. Okay. And so this is minus 4 over 7 squared, or 49, minus 3 over 7 squared. So this is minus 7 over 7 squared, or minus 1/7. Okay. And so we got an answer for when we computed our Jacobian. We got something that's always negative, so we're going to have to remember when we put it in underneath the integral for the change of variables formula that we're taking the absolute value of this thing instead. Okay, but now we have everything set up. Okay, so what was the integral I was originally asked to evaluate? Double integral over r of 7xy dA. Okay. So now it's time to use my change of variables formula. So the double integral over r of 7xy dA using change of variables. This is the double integral over that region S I found of 7. I need to plug in my transformation t. Well, there it is. So for x, I plug in 1/7 2u plus 3v. For y, I plug in 1/7 u minus 2v. Okay, and so this is 7 times 1/7 times 2u plus 3v times 1/7 u minus 2v. Okay. Times the absolute value of the Jacobian, which was minus 1/7 dA. Okay, so let's do a little bit of algebra to clean this up here. So cleaning this up just slightly, I'm going to have, so the absolute value of minus 1/7 is 1/7. That cancels with this 7. And then I have 1 over 7 squared to move outside, so that's 1 over 49. My region S, just to remind you, looked like this. And so we would have my inner integral, if I'm treating this as vertically simple, my inner integral would go from minus 2 to 2. Outer integral would go from 1 to 3. So this is the integral from 1 to 3, integral from minus 2 to 2 of what is left here. So this is, let's go ahead and just expand this in our head here so we can save some paper space. So 2u times u is 2u squared. That's going to be the only u squared term. And then we're going to have a minus 6v squared term. And then the mixed term is plus 3uv minus 4uv. So that's going to be minus uv. So this is going to be 2u squared minus uv minus 6v squared dv du. Okay, so let's do this integral with respect to v first. So this is 1 over 49 times the integral from 1 to 3 of, this term doesn't depend on v, so this is just 2u squared v. That's the integral of that thing. What is the integral with respect to v of minus uv? Well, that's minus 1/2 uv squared. All right, just using my power rule. And what is the integral of minus 6v squared with respect to v here? So this would be minus 6v cubed over 3. So this is minus 2v cubed. And this is evaluated from minus 2 to 2, evaluated in v. Right. Okay. So let's see how this works here. So here I would, at the top, I would have 4u squared. So yeah, 4u squared minus 2u minus 16. And then from that I would be subtracting minus 4u squared, but I'm subtracting it, so I would get 8u squared. the middle term, since I'm squaring it, doing this evaluation, the middle terms would cancel since this is symmetric. And so I would be left with minus 16 here. And there's 3, so it'd be minus 16 minus 16. No, wait. Oh, yeah, it would be, this would be 16 times 3 minus sign, so that's minus 16 still. So this would be 1/49th times the integral from 1 to 3 of, this would be 8u squared minus 32 du. And now I do this term by term here with respect to u, so this is 1/49th times, this would be 8/3 u cubed minus 32u, evaluated from 1 to 3. So let's write this one out. So this is 1/49 times the upper evaluation is so 8/3 times 3 cubed minus 32 times 3. This thing minus 8/3 times 1 cubed minus 32 times 1. Okay, and all of this is times 1/49 here. So 1/49 times what goes here. So let's see. So 3 cubed divided by 3 is 3 squared. So this is 8 times 3 squared. So 8 times 9, that's 72. That's 72. Minus 3 times 32, that's minus 96. Minus 8/3 plus 32. Okay, so let's see. 72 plus 32 is 104 minus 96 is 8. So this is 8 minus 8/3. So if I put both of those over thirds, this would be 24 minus 8/3, so 16 over 3 times 149. 3 times, or 1/49. 3 times 49 is 147, so this is 16 over 147. Okay. Okay. Yeah, so I think that works out. Jacob was saying in chat, worrying about the sign. I think this is the right. And I was spent more time doing the arithmetic than actually carrying out the integral. So it's usually not well advised to do that, but I wanted to make sure it worked out all right. So anyway, as far as like conceptually, understanding the material, you are done and you've done a good job once you get to this point where you have written it as this double integral. Well, now you've reduced it to the stuff you've been doing for a few weeks now, right? So that's that. Okay. I'm going to write out a couple of other examples of when you might use change of variables, but I'm not going to fully work them out. I'm just going to show you how this would go. Okay, and it's on you to work them out because I may put them on your next exam or something similar to them. Of course, if I ask this as an exam question, I may not tell you anything. I may not say use change of variables. I may just say do this, compute this double integral. And if you try to do it, in the bad way, well, you're going to be sad. Okay, so let's evaluate the double integral over the region R of x squared plus y squared dA, okay, where R is the closed elliptical disk which is x squared plus 1/4 y squared is less than or equal to 1. What does that look like? Let's draw that. this closed elliptical disk looks like this. Okay. Where here's 1, here's -1, and here's 2, and -2. So here's your R. Okay. Now, you could say, well, what's wrong with this R? Is it bad to integrate over something like this? Well, not necessarily. This is not necessarily something that's bad, but still, I want to do this in another way, because the other way that I want to do it will allow me to use polar coordinates. And now I know what you're thinking. You're saying, oh, wait, polar coordinates is one example of a coordinate, of a change of variables. So you're going to do a change of variables so that you can do another change of variables. And that's right. That is exactly what I want to do. Okay. So how does this go? Well, idea. So come up with a change of variables that transforms the ellipse into something better. Okay. So the hint that I've given you is that I want to use polar coordinates here, so it's more or less obvious what the something better has to be once I say that, right? So I want to change this closed elliptical disk into a circular disk, right? So I want to change that boundary ellipse, which is the ellipse x squared plus 1/4 y squared is equal to 1. I want to change that ellipse into a circle. So how do I go about doing that? Well, let's think here. The idea comes from looking at this ellipse and saying, well, it would be a circle if that 1/4 wasn't there, right? So if that 1/4 is not there, it would be a circle. So how do I get rid of that 1/4? Right? What if I say, let x be equal to, say, u, right? What would y need to be equal to in order to... Why did I pick u here? I mean, I could have picked v, obviously, but I picked u here just, and not like 2u or 5u or 7u or 3v or whatever, because this factor, whatever x is, doesn't need to be changed, right? There is no bad coefficient here, but there is one here, and I want to get rid of it. How can I get rid of it? I can let y be what? That's something that I could let y be equal to here. Well, if y is 2v, right, then what do I get? Well, let's see what this becomes under that transformation. So x squared plus 1/4 y squared is equal to 1. This becomes x is equal to u, so this is u squared plus 1/4 times 2v squared is equal to 1, which is u squared plus, squaring this is 4v squared, so this is 1/4 times 4v squared is equal to 1, and so this becomes u squared plus v squared is equal to 1. What is that? That's the unit circle in the UV plane. So here's S. So this transformation T, this is my transformation T, takes unit circle in the UV plane and moves it to this region, this elliptical disk region in R. Okay. All right. And so once you've done that, what is the idea? All right. So then I use polar coordinates to compute the UV integral. And so let's just write out what it is that happens here. Right. So by change of variables, I would have the double integral over R of x squared plus y squared dA. So this becomes the double integral over S, the double integral over S of plugging in here. I'm plugging in x equals u and y equals 2v, so x equals u, this is u squared. Y is equal to 2v, that's 4v squared, times the absolute value of the Jacobian of that transformation, dA. Okay, but this S is the closed unit disk, and so the easiest way to deal with that is then use polar coordinates. Okay, so then I would do this in polar coordinates, letting u, so use polar coordinates. But we're using polar coordinates not with respect to x and y, but with respect to u and v. So I would let u be, r cosine theta, and let v be r sine theta, right? And proceed like that. So left to the viewer. Okay. So hint, hint, I may put a very similar thing on your next exam. Okay, another example. Right, and say that in this case, so in most of these examples, we have used change of variables to save us from a bad region. Okay, but change of variables, so COV, can also save us from a bad integrand. So we have only seen examples of it saving us from a bad region we didn't want to integrate over, but it can also save us from a bad or undoable integrand. So what's an example? What if I was asked to evaluate the double integral over R, where R is some suitable region that I'm not going to even write out, of like sine of x minus y over cosine of x plus y dA. So let's say that I have this where maybe R is some region. Okay, that will be, convenient enough for this sort of example. What is the idea here? Well, the idea is to let u be x minus y, let v be x plus y, and do a change of variables to see if what you get out of this ends up being nicer. Okay, in some way. Okay, why would this be nicer? So why would this be nicer? Why would doing a double integral over some s of sine of u over cosine of v dA be nicer? What's the problem with this integral? Say that I wrote this out, right? So I wrote dy dx here. So I have to do an integral with respect to y first. The problem is that y is tangled up in both of these things, right? Which is bad. I don't like that, right? That makes it hard to do. But if I do a change of variables where u is x minus y and v is x plus y, then when I rewrite this expression and go through this whole process, in my integrand, I have sine of u over cosine of v. So when I do this double integral, if I have a du or dv here first, I can integrate each of these terms one at a time. right? So algebraically, this is a nice way of some trickery that can make all of this work out much better for you, right? So this is saving you from a bad integrand, as I said. Okay. So questions about any of that? If you do have any, let me know. So one more fact that I'll mention. There is a change of variables formula for triple integrals as well. Okay, what does it look like? Well, it looks exactly like you would expect. So you still have a transformation. So you have a transformation that is given to you by three functions now. So x is equal to g sub 1 u v w. Y is equal to g sub 2 u v w. Z is equal to g sub 3 u v w. We can compute the Jacobian of this thing. It's defined in exactly the way that it should be, but it's the Jacobian, it's the determinant of a 3 by 3 matrix, unfortunately. So Jacobian of u, v, w is the determinant of the 3 by 3 matrix x sub u, x sub v, x sub w, y sub u, y sub v, y sub w, and z sub u, z sub v, and z sub w. Okay. All right. And so, with those things written out, the change of variables formula is the triple integral over some region. I guess we'll call, since we usually reserve R and S for 2D regions, I'll call this over regions D and E. So we'll say T maps a region E in UVW space. So this is UVW space to D in XYZ space. Okay, and so this is a triple integral over D of some function f of xyz dv. This is the triple integral over E, which is the region that maps to D under this change of variables transformation, of f with all these functions plugged in. I'm going to suppress the notation because it's too long. So I plug in g sub 1, g sub 2, and g sub 3, those functions of UVW here, and that is multiplied by the Jacobian in this case, dv. So it works out in the exact same way. And the main reason I wanted to say this is for the following fact. So let T be spherical coordinates. So the spherical coordinate transformation. So what's the spherical coordinate transformation? So x is equal to what? So it's equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. Okay. So each of these are functions, right? So this would be my g sub 1 of rho phi theta. This would be my g sub 2 of rho phi theta in that previous thing that in that previous notation that I had on the last page. Okay. What is the absolute value of the Jacobian? What do you think that is? You already know. know how it works out. Why did you already know this? Because this is the factor in spherical coordinates. When you're doing a triple integral in spherical coordinates, this is the factor that shows up, right? So this is the spherical coordinates correction factor. Okay. All right. So that is the last of the integration stuff that we're going to be doing for now. So in the chapter 14 material. So we're about to head into chapter 15, which, if again we're following this analogy with Calc 1, in Calc 1, after you had the basics down, which was like limits and continuity and stuff, then you talked about derivatives, right? And then you use those derivatives to analyze functions. So that was our chapter 13 that we went through with all our partial derivative stuff. Ultimately, culminated in Lagrange multipliers and being able to talk about relative extrema. Okay. Then in Calc 1, you introduced the integral and how to compute some basic integrals, some basic definite integrals, approximating them with Riemann sums, the definition of the definite integral, computing integral as an antiderivative, and then ultimately using substitution, right? This is what you did in Calc 1. So then we have been doing that with double integrals. So then the very last thing that you did in Calc 1 was the fundamental theorem of calculus, right? FTC, both versions of FTC you went over. So we haven't done that yet for our double integrals, but we're about to. So that is what chapter 15 is basically. But before I head into that, I'm going to do a brief detour, which has to do with parametric surfaces. This will let us go through chapter 15, basically not having to go back to chapter 14 stuff. Usually that's how I do it, but I decided this time I'm actually going to finish chapter 14 in its entirety. So next time we will start and finish 14.9, which is parametric surfaces. So what is the idea with parametric surfaces? So the same idea that we had for curves, right? So in the plane, maybe when I ask you to draw a curve, you draw something like this. And that's fine, that's nice. What's particularly nice about this is the graph of a function, right? But that's not really what a more general curve would look like. A more general curve would look like this. Right? All right, and put your axis wherever you want to here. So if this is my xy axis, if you like, then the problem is this curve is not the graph of a function. Okay. Well, we get around that by, instead of talking about curves that are only graphs of functions, we talk about curves that are parametrized by some parameter t. So that a single point here is described as the value at some parameter t of two functions of t. Of course, another way of writing that is just like we did in previous chapters. This would be x of t I plus y of t j for t living in some interval, right, a to b. Okay, this was the idea. Okay, and of course we even talked about this curves in space like this. Okay, and the benefit of doing it this way was this vastly expands the class of curves you're talking about, because now you can talk about things that look like this, right? You're not just restricted to curves that are the graph of a function. And of course, even if you want to talk about curves that are the graph of a function, they're a special case of parametric curves. Okay, and so doing this allows you to do all the old stuff you were doing anyway. Okay, so this is definitely the way to go about it. So I want to do the same thing with surfaces. If I ask you to draw a surface, right, in some 3 space, you're likely going to draw something like this maybe, right? Maybe you won't. Maybe you'll draw something else, but maybe you'll draw something like that. Well, this is a perfectly fine example of a surface, but again, this is the graph of a function. There's plenty of surfaces that we're interested in that don't arise like this, so sphere. Not a hemisphere, right? Not just part of a sphere, like the entire sphere. This isn't the graph of a function because it fails the vertical line test, right? So it's not the graph of a function. I could think about it as having a top function and bottom function, but that's not really the same here. I want to be able to describe this parametrically. Okay. There are other examples. There's the helicoid, which, let's see how bad my drawing of the helicoid is going to be. So let's take the helix and add a width to it, basically. So if you think of this helix kind of like circling around here. Oh, I should have left myself room. That's okay. I'll leave myself a gap here. Okay. But then you add like a width to it so that it's doing this sort of thing. Here, let's see here. So I want to, oh no, this is bad. This is why I was, not into like art and stuff. Okay, that's really pretty bad, but think of the helicoid like, this spiraling ramp. Okay, but so it has a width. This is not just two dueling helixes. This thing has a width, so this is what it looks like. Okay, so here's my helicoid. So a thing like this that spirals over itself, this is a surface that is not the graph of a function clearly because it fails the vertical line test actually infinitely many times, right? It's forever spiraling above and below itself. But this is the sort of thing that by the end of this section 14.9 we'll be able to describe and do calculus on. Okay, and we'll be able to do that by describing these things parametrically. Okay, you actually have already seen a parametric description of the sphere, you just don't know it yet. Okay, the grand idea that allows us to do this is actually not that complicated. The grand idea is to add a parameter, and that's it. All right, so curves in the plane or space were parameterized by a single parameter. Surfaces will be parameterized by 2 parameters. Okay, but now you see why we had to wait to talk about this, because we're talking about functions of more than one variable. Each of those parameter functions in every slot is going to be a function of 2 variables. And so that right there tells you that we had to wait until now in order to do it, because we had to wait until we fully understood how to deal with graphs of function, or just functions of 2 variables anyway. All right, so anyway, that's where we'll start on Friday. So on Friday we should finish parametric surfaces stuff, and then next Monday we will start chapter 15 material. Okay, so we're in the home stretch. Anyway, so I will see you all on Friday. Oh, I didn't post a reminder about the MATLAB. I'll post a reminder about the MATLAB tonight. All right, so be looking for that if you haven't turned in your MATLAB yet. Okay, anyway, I will